Lewis is a fine product of the University of Nairobi, Kenya, and Stellenbosch University. And he's currently enrolled in a PhD in electrical engineering at Stellenbosch, where his research interests include distributed energy resources integration studies, rural electrification, low voltage distribution network planning, and energy policy. Lewis works as an engineer at the Center for Renewable and Sustainable Energy Studies. So he's a fine product with a good pedigree. Lewis, I'm really looking forward to hearing what you are coming up with our friends from Stellenbosch University. So, colleagues, I will hand over to Lewis without further ado. Lewis, the floor is yours.
Wow, thank you. Nobody has ever introduced me like that. Thank you. My name is Lewis Waswa. I'm a PhD student at Stellenbosch University under Dr. Bernard Becker and Dr. Justice Chihota. So today I'm going to share with you part of my work, which we are doing in terms of developing a framework for conductor and transformer size selection for active low voltage distribution networks. Very brief, I'll just run through these things because I know you know them. This is the content of my presentation. I shall introduce the subject as I know it. Then I shall talk about the characterization of passive distribution networks, then the transition towards active distribution networks and the requirements thereof, as well as the overview of the proposed methodology that we've come up with, or rather which is still ongoing. And I shall demonstrate a case study we've done and then conclude. So what is happening? We know that the distribution network is actually changing because of the increase in the amount of DERs that are connected on the networks, especially in a behind the meter configuration. And this is changing the operation of the networks as we know them from passive to active. And with them, there are several challenges, technical challenges that arise. That is in terms of increased voltage rise, transformer and conductor thermal loading, as well as introduction of reverse and introduction of all these new technologies from rooftop PV and it's not going to like change to build a new system for this change. The change is happening in flux. So what do these changes actually mean in the general planning context? So just as a revision, I will talk about the general planning context, which has reliability planning in it, mainly concerned with generation, and then we have network equipment design, which specifically handles the selection, placement, sizing, and which is our primary focus here. Then it looks at the loading condition of our network, the scenarios that are going to we are seeing on our network have implication on the performance of the network, as they directly touch on the distribution network design objectives, which in this case is basically to select your various network equipment to satisfactorily supply your loads within the set quality of supply standards or limits. So we have categorized these network design, distribution network design into several aspects, which include the primary aspects as well as the secondary aspects. And we are focusing on the primary aspects, which include conductor size selection and transformer size selection. The objective, so the transformer and conductor size selection are referred to as TSS and CSS herein after. So the objectives of your CSS or TSS process is in twofold, as we all know. It's either technical or it's economic. And mainly the technical objective is usually concerned with the loading, either of the transformers and the conductors, as well as the quality of supply standards, which have got to do with voltage rise, as well as voltage and balance, among other issues. And your economic objective would be basically to look at what is the cost aspect of your design. Is it affordable? Can we meet it? As we even say that it's technically feasible. So I'll look again at the network. What is the basis of designing the existing network? And as you can see, we have unidirectional power flow, where you have your power plant, then you have your transmission system, you have a transformer, all the way towards the distribution network, and then to your end customer. Also, basically, the existing distribution networks were designed as such, by means of having predictable load profiles and patterns based on feeder maximum demands, which is probably which factors in your peak loads And all these values are deterministic. Even the load values that you are going to use are usually deterministic or static. And they apply a deterministic power flow, which is much more simpler. Then lastly, there is no consideration for indispatchable distributed energy resources in the planning process or even in the sizing of the equipment that are going to be used on these particular distribution network. There is a transition that is happening. So you have this particular system, which is passive, transforming itself into an active distribution network. And what is the operational basis of active distribution network? So you ask such a question in terms of how is your general passive distribution network changing towards the active distribution network, and what is happening as that happens? So we have an introduction of bidirectional power flow, in which case you have electric vehicles charging, you have photovoltaic integration, wind integration, and all these basically indispatchable, which means they generate power when they do. And if the load is not sufficient enough, they inject the rest of the power into your network. There's also uncertainty of load profiles and patterns, which has been occasioned by new technologies as well as demand side management, where your general customer can manage his loads and decide to use his DER rather than using your grid. So you as a distribution network operator no longer has the monopoly of the knowledge of what you expect at certain times. So you also have uncertainty in DER output, which is basically related to both the variability and the intermittency that is associated with PVs and wind and others, as well as the time of use patterns that you don't know from your dynamic loads. And just on the same point, we have pervasive increase in the indispatchable behind the meter generations and dynamic loads. And the dynamic loads are characterized by time of use patterns, which are hard to actually predict, which is also forming our next part of the study. So one of the key other aspects is uncertainty in allocation of these DERs. And the reason why it is highlighted in red is because the allocation problem is very pervasive on the low voltage distribution network, where you as the planner has no knowledge of the type, of the capacity, or the node and phase that the customer is going to connect that particular DER, or rather say DG, on your network. So while you may have the power to make a decision on the total capacity that may be installed on a particular feeder, you do not know the distribution thereof. So you have no ability to tell what is the future loading condition and what is the nodal loading or the specific branch loading. The nodal voltage or the specific branch loading on your feeder. So one thing that I find very interesting is that while this transition can be relatively in an easier manner managed at other network levels, at low voltage networks, it's very gradual and continuous as well as uncontrolled. This is to say that the guys who want to install PV on your distribution network are not waiting for you to develop a new network and tell you, so that they can connect. They are connecting on the originally passive network, which was not designed for those connections. So they are transforming your grid into an active distribution network, which therefore impacts its performance. So as you evaluate, probably with the aim of improving or enhancing more DER uptake, you have to think of how will I reinforce this particular network, or how, if you're going to create a new network, you have to think of what is the best approach through which we can size, say, conductors or transformers that are going to meet the impacts that we expect from this level of penetration. So that's the transition we are facing, and it's happening in flux. It's not something that people are waiting later to say, oh, now we have a network, now we want to connect on that new network, which was designed for DERs. So the implication of this transition, why is this important to power system engineers and planners? One is that DERs basically impact the technical as well as the financial operations of the networks. We are more focused on technical here. And as I've noted before, the technical impacts may include both voltage rise as well as increase in voltage rise, increased conductor and transformer loading, as well as phase unbalance, and even reverse power flow. So in essence, it means that if you are going to decide that we want to have a grid that takes this amount of DERs, DER will affect your future loading, and by extent, it will affect the quality of power you are supplying to your customer. So in general, it affects your performance, the network performance. So secondly, it also has an implication on the equipment life cycle costs. For instance, increased DERs would generally limit the network equipment performance if they are not well controlled or their impacts are not well mitigated. The other thing we need to also know is that both transformer size selection and conductor size selection is relevant in the new electrification projects where you are actually planning for DERs. For instance, if you have a plan for a network to host 50 kilowatt peak, a feeder that needs to host 50 kilowatt peak or 100 or 200, you will know that the hosting capacity of that particular network is directly linked to the size of the conductors and the transformers it's going to have. And that is also linked to the impact of the type of DER that you are going to install on that particular network. What we can conclusively say is that the passive methods are inapplicable in any planning scenario that may involve DERs, just based on the fact that they were not actually they were not built for distributed generations or to handle, an active distribution network-based kind of operation. So in a summary, I can say that for existing networks, DERs increase the need for network reinforcement and capacity enhancement, where the planner has or rather wants to achieve a certain DER penetration target. And for new electrification project, it becomes very imperative that appropriate modeling should be conducted in order to avert the technical challenges associated with, or rather the technical challenges that we see occurring in networks that were not originally designed to cater for DERs. So just as a recap, the shortfalls of the passive distribution network planning methods, and these we are looking at what are the features that ADNs have that passive networks don't have. One, active distribution networks should consider indispatchable DERs, which have two things, both output and allocation uncertainties. I've explained allocation uncertainties in terms of the capacity and the placement, in terms of node and phase placement as well, and the output, which has got to do with the variabilities and the intermittencies that are associated with each of the DERs. Two, there is no consideration for bidirectional power flow. Then the introduction of uncertain and variable distributed generation and dynamic loads was not considered in passive networks. And all these uncertainties from different sources require extensive probabilistic modeling, which has not been seen elsewhere in either the literature or in the methods that have been applied before. The importance of CSS or TSS in the active design of distribution network design. As I've said again, that the conductor size selection processes and transformer size selection process is very critical in new electrification projects where DERs are being considered, as it's closely linked to the network hosting capacity. It determines whether your design network can actually meet its objective. And it's very critical in active low voltage distribution networks where you have most of your behind the meter DGs and dynamic loads being connected. And one of the reasons as to why that's the case is because a lot of low voltage distribution networks are not usually monitored by the distribution network operator. And that means that the conditions of your network in an LV distribution network may not be known and will be exacerbated when you have a high penetration of DERs. So what are the critical factors that require attention in this CSS or TSS process for LV ADNs? And three of them, probably the ones we've picked out, the DER allocation, DER output, and load variability modeling, and then DER time of use pattern modeling. So as you can see, it's a multi-level uncertainty that we must consider. And in considering it, we also wanted to meet the following requirement. We have to ensure that whatever is sized, the conductor that is sized, the transformer that is sized, can accommodate the expected load. It can also accommodate the impacts of different DER types under different operating scenarios and time of use patterns. And the selection must meet the quality of supply standards. So I'm just going to go briefly fast through the methodology that we've proposed. So this is basically the rubric, the general way we're looking at this model. And the model has an input process output approach where you have the first segment being your input modeling, the second segment being your processing of those input, and then the third modeling being, working on your output to carry out an iterative resizing process, which then yields your technically viable conductor. The last part would be an optimization process where you test it against cost objectives, like a normal, the normal conductor size selection methodologies that have been done before. So the arising scope in these is basically probably 3 or 4. One is we just need to carry out a conductor size selection, develop a framework for that. We develop and test a conductor size or transformer size selection framework. And then we have an input modeling. So in which case we are going to evaluate to model different DERs and DER combination. So in these we are looking at what are the appropriate models for each DERs and the loads, the DGs and the loads, as well as what are the appropriate processes of combining different DER models. What are arising scenarios? What are the arising scenarios and how should each be modeled? And lastly, probably what is the most likely scenario for, in this case, for South Africa? Which one would be the appropriate one to be considered in terms of you creating a sizing approach? Would you consider a combination of EVs and PV? Would you consider a combination of PV and battery energy storage, or would you just consider PV, for instance? So those are the questions probably we are grappling with at the moment. And then we have another segment which involves the integration of these DERs into the CSS framework that has been developed. So in this case, we are also thinking about multiple DER allocation integration in our model, because it's easier to carry out allocation of a single DER. But now when you have, say, 1 or 2, you have to figure out how to carry out that allocation based on, several factors, including how prevalent is the type of DER that you are looking at. Lastly, we have an optimization framework, which is, as I've indicated, is the last part of our methodology. So I look at our case study. So this is basically the way the method looks like, but I'll just move fast to how each of the segment works out. As I've said before, we adopt an input process output approach in terms of the input modeling, and then we will look at the process modeling and lastly the output processing. So to just come back here, 3 elements are considered in your input modeling. You have either the feeder model. Sorry, I didn't say this. This is a proposed method that we applied on the CSS, not TSS. So we have dealt with conductor size selection for one of our papers, which we have written. And this is the process that we follow. So just bear with me and I'll take you through it. So the input modeling process, as I've indicated before, then there is the process modeling, and then there is the output processing. And so that in this case, we are looking at 3 things. If you are considering conductor size selection, you're looking at your feeder model, you're looking at your load model in terms of the PDFs of the load model, and then you are looking at your DER models. So this can be PDFs from either solar PV, EV charging, or wind output. So in that case, the diagram on your right illustrates in the red, the figures in the red show you what we are basically dealing with. Then in your process modeling, there are 2 things that you carry out. That is, one is a grid impact assessment, where you assess the performance of your designed starting feeder. For instance, you will have a passive feeder with which you're going to test its performance based on incremental PV penetration. So this is a case where you are basically building a new electrification system. The approach would be different if you are to consider a process where you have a feeder, an already feeder, so you don't have to basically test to have a feeder model, because in this case you'll have the feeder. So here we have a grid impact assessment where you assess the adequacy, the performance of the designed feeder to test its adequacy in meeting your desired penetration level. So you're basically asking, is this feeder, can it meet 100 kilowatt peak? Can it perform within the quality of supply limits at 100 kilowatt at full uptake, which is 100 kilowatt peak, for instance? And then in the same process, we carry out conductor validation, where we assess the compliance of each feeder in terms of its branch and node performance. So you note that we are specifically looking at each element in the feeder. So we are not just piling the feeder together. We are specifically picking out how does this particular branch 1, branch 2, branch 3, and branch 4 perform in terms of conductor loading, and how does node 1 to node N perform in terms of voltage. And in this case, we obtain risk-adjusted performance indices from our analysis, which we then use in our output processing. And these are basically your conductor performance index and your node performance index that are obtained as indicated in the equations below. So the output process does several things. One, it determines the performance of each element based on the NPI, and then it estimates the replacement for the non-compliant conductors by scaling down the resistance of that conductor using the CPI and the NPI. So this is a whole process that we also did for our study. So a replacement conductor close and lower than the resized is selected, and then the feeder model is updated. And our stopping criterion is just to ensure that the node performance index and the conductor performance index is less than or equal to 1. And at that point, we return our resistive values and the corresponding conductor sizes, which give us that. So this was our case study. These are we have our illustrated or rather tested feeder. In terms of the number of nodes, we have 7 nodes. Each node has 3 single-phase customers, making up. So we have 7 customers, 7 nodes, and each node has 3 single-phase customers, which make up about 21 customers. So this is a simple feeder that we tested our method with, and those are your input model parameters in terms of your load for your winter and summer periods, your ADM in kVA, as well as we also modeled PV using the beta parameters, and you can see the representation in there. So on your right, top right, you see your performance, the performance of your initial passive feeder. And as you can see, it's well sized. It's because the voltage drop does not go below 10%, and your loading does not exceed 100% as well. So the table in case 1 just shows you the passive design, the initial passive design, and the resistance of the selected conductors for each section, as well as the thickness, or rather the cable size, the cross-section in terms of square millimeters. Case 2 shows you the results we obtained after we used our method. After we used our method in terms of resizing iteratively, and the resistance that we also obtained for that particular analysis. So something to note here. So these basically scatter plot illustrates to you the performance, the voltage performance in terms of your feeder maximum voltage, and that's on your left. On your right, you have your conductor loading in terms of your feeder maximum currents as well. So these two scatter plots are the very ones that we use in our process. So what I can say here is that based on the voltage rise performance, the feeder can accommodate up to 100% of feeder maximum demand, which is approximately 48.5% of the desired penetration level. And if you consider the conductor loading, you have about 160, which is around here, 160% of the FMD. And if you're thinking about saying what is the capacity, what is the feeder hosting capacity, then you compare those two, and you can only get it based on what is the lowest value obtained when you have two parameters that you are assessing, that is your voltage rise as well as your conductor loading. So in this case, your voltage rise returns a lower value compared to your conductor loading, and therefore that's the value that you can give as your hosting capacity before you start your iterative resizing process. So based on this, we can say that the feeder cannot accommodate the maximum penetration, or rather it cannot have a maximum uptake, and would require adjustments for you to basically meet that. Then also, something very interesting is that if you look at these particular performance, you will note that uniform loading is basically not the worst case scenario considering the voltage rise. So uniform loading would be achieved somewhere here, but your worst conductor, I mean voltage rise performance, is somewhere where we have your PV here. That's basically probably associated with increasing voltage unbalance. As the voltage unbalance increases on your feeder, there's also an increase in voltage rise. So therefore, if you are to just say we are going to size at this last position without necessarily considering the incremental performance of your feeder, you are likely to get wrong descriptions. You are likely to get a wrong feedback in terms of your sizes. Okay, so you can also get other from what we have from our tool. You can get to see the performance of your feeder in terms of each node voltage as well as each conductor current loading. So these box plots would show you how, like for instance, here is the node performance, and here is your conductor, or rather the branch performance. So it can illustrate to you that this particular conductor number 1, this particular branch number 2 are actually violating your performance because they're above 1. If you consider the performance of your voltage, you can see that your nodes are 5, 6, and 7 are actually above your 1.1 mark. And that basically helps you to identify which of all these conductors that we have in here should be replaced, or instead of just saying we are going to replace all of them. So when we carried out a resizing process, this is what we obtained in terms of voltage rise and in terms of conductor loading. As you can see, based on the 5% risk trend line, both the conductor loading and the voltage rise limits actually the conductor is compliant. I mean, the feeder is compliant for both voltage rise and conductor loading. So as I've said before, you can see from your box plots that nodes 5, 6, and 7 violate the voltage rise constraint at 5% risk, and branches 1 and 2 would violate the conductor loading constraint at 5% risk. So subsequently, you need to apply an iterative resizing process, which we have explained before. And as shown in the scatter plot, at 5% risk evaluation, the feeder can accommodate the desired penetration without violation after resizing. So we tested this method on other levels, and that was at 6 kilowatt peak, and we also tested at 10 and at 12. So what is interesting is that even your passively designed feeder can accommodate at least 6 kilowatt peak per customer at and the 5% risk response is shown here, which means it does not violate the constraints if each customer has 6 kilowatt peak, and this is the same for your conductor loading. So this can be attributed to your design risk when you are designing your network. We factored in a 2.5 risk in our power flow analysis, and then we factored in another 2.5% in the interpretation of the scatter plots. So that made up the 5% risk response. But because of the risk that we had inculcated in our initial passive design, your feeder can accommodate a given level of PV. But as you increase your PV penetration per customer, your PV capacity per customer, your need for resizing also increases. So several highlights. I can say that the initial, as I've said, you can see that there is a capacity which your feeder can actually host without needing adjustment. and beyond certain points, your initial design will be altered to accommodate your required DERs. So, in conclusion, we have actually proposed a probabilistic conductor size selection method where we formulated and tested it and validated it. The proposed methodology considers, which is very interesting, considers load and DR output, which is not usually, in terms of considering the probabilistic modeling of these particular components and allocation uncertainties, which I've mentioned as crucial in this particular aspect. And then the method presents a risk-based conductor-specific analysis. And by conductor-specific analysis, I mean you can get to see the performance of each of your node and to see the performance of each of the branch on the distribution feeder. And that performance can help you to understand which side do I want to actually resize, or which part is constrained and which one is not constrained. So this method accommodates for uncertainty and therefore is relevant in distribution planning, especially at low voltage distribution networks, where you have no idea what node or which customer are placed at whichever point is going to install PV. Lastly, just to reiterate again, the method is applicable in new electrification projects where DERs must be accommodated. And we've also written a paper looking at the application of this method in the reconductoring of distribution networks, especially where you have a feeder and the distribution network operator thinks it's important that we consider increased DER on this particular existing network. So this method is also applicable in that particular framework. So further work, which is, I think, very important and on my mind here, we also need to carry out a formulation and testing of the method using different DER types and combination. For instance, whether it's important that we test it with how the method performs with if you have EVs and PV, or ESS and PV, and what are the models that you're going to need, and how do you integrate all those models. That's part of the work that we have not done. And I hope I can get feedback from the load research chapter on these particular issues. Thank you very much, and it's been a pleasure. Any questions?
Thank you, Lewis. This is a very interesting discussion that you've raised, and I think with each new solution, we kind of step into a new space where it opens up a whole lot of questions, and that is typical of these white spaces. I would like to just give Tulani a chance to voice his question, which is popped into the chat box. Tulani, would you like to come in and give it the context?
Sure. Thanks, Marcus. Thanks, Waswa. I mean, the question read, it's around, is there a guideline for a threshold for the DERs to say a network can possibly host so much percentage of the feeder maximum demand without the need to change, or without it impacting the network as is? And of course, how would that then compare to the current NRS limits, and being cognizant of the fact that it will differ from one network to the next? But as a guideline, is there an indication of what percentage hosting can one accommodate without necessarily impacting on the existing network?
Thank you. I'll probably respond to your question using this diagram here. Firstly, I'm not aware of any particular guideline that says this is what a network can host in terms of your feeder maximum, the percentage of the feeder maximum demand. But what I think this tool would help is to help the distribution network operators to just be aware that their network can host this particular amount. For instance, if you look at what I've said here, based on your VR performance, you can host 100% of your feeder maximum demand. So I can't really recall what the feeder maximum demand was, but at around 100%, if you have your feeder maximum voltage per unit voltage being looked, the constraint is at 10%, you realize that at 100%, which is here, you probably have not violated those particular conditions. So just as a response tool, which you can use to assess what's the performance of my network as I increase DERs, this tool can tell you what is the capacity, the hosting capacity of your network. But I can't say that there's a way, there's a standard to it. I haven't seen a standard to it. But if you consider it, I think it would be greater than what the NRS would state to you, because NRS would give you a very conservative figure to just protect the network from extreme events, maybe. I don't know. But you can actually apply this particular tool to testing your network performance. And once you get the network response, you can assess what is the limit before you violate the constraint you're looking at. Okay.
Thank you, Lewis. And Tolani, would you like to perhaps just fire off your next question?
Yes.
Whilst you're on the table, thanks.
Thanks. I thought I saw on the slide that you were talking about the grid impact assessment.
Yes.
I thought I saw something about a full load, and my question was, wouldn't we then want to do the assessment at the lowest load with maximum generation? Unless if I misread that.
Okay, so probably I should explain from this, then I shall go on the full uptake side. So as a distribution network planner or operator, you want to design a system that can meet a certain threshold. So if you say that my planning is supposed to meet 100 kilowatt peak, then it's distributed in such a way that each customer is going to have a certain threshold, such that your full uptake is at 100. But that's not a prerogative. I don't know. It's not a prerogative of. It's got nothing to do with your feeder maximum demand. It's just that your penetration is being calculated based on your feeder maximum demand. So I don't know if I'm answering properly, but the point is, in the end, you want to size a system that meets a given penetration, and the penetration will be defined as given here, your PV versus the feeder maximum demand, and that gives you your percentage threshold. So to ensure that your risk trend line is below that, that's the process we're giving you. But if you want to ensure that your system is actually just compliant, you are going to test your feeder response as opposed to you resizing the system. So for instance, what we have here is a passive feeder. If you impinge continuously if you increase the PV penetration on that particular feeder, you gain these response that we have from this point to this point here. Now, as your penetration increases, you have your voltage rise increasing up to a certain point when you attain your maximum penetration. So your penetration is an independent factor, but your penetration is generally increasing. It will exceed your acceptable feeder maximum demand at a certain point, because at 100%, that is where your feeder maximum demand. You want to design your system from the passive to an active one, such that it can accommodate the given 168 or 200 kilowatt peak of PV. And at that point, it should be somewhere here. And when we move, and then when we do the resizing, you have to ensure that your constraint is actually met. And the constraint is only met if your 5% risk line, or whatever percentage you choose, is actually falling below your particular index that you want to assess, which in this case would be, say, the voltage performance. I don't know if I'm answering my question or I'm answering yours.
I'm not sure if you answered my question, but the point that I wanted to make is the voltage rise that you see at when your feeder is fully loaded will be different from the voltage rise that you see when the feeder is slightly loaded. So in you wanting to determine the impact of the penetration on your feeder, you want to, in my mind, you want to assess that impact when you have the adverse impact from your PV penetration, which will be when your feeder is slightly loaded.
The adverse impact, I would think, is when your feeder is fully loaded. Am I right?
I think Solani is pointing out that when your feeder is sort of almost not loaded, that might be more adverse in terms of voltage rise. It's not in terms of feeder loading.
Yes.
Come again?
I think what Solani is trying to point out, and it's quite a good point, is saying that your most adverse cases of voltage rise may occur when your network is lightly loaded, and yet you have full contribution of these DER systems.
Sorry, gentlemen, I think we have a slight confusion in terms, because I think Solani, Marcus, and are thinking of loaded in terms of consumers drawing a demand, and Lewis is talking about actual amps in the feeder. So yeah, so when the load is lower, it is more adverse, but then your voltage, because otherwise some of your generated PV will be used in it by your loads.
Yes.
Yeah.
Did you get that, Lewis?
No, I didn't.
It's a bit of a mind shift. Maybe you can try again.
Okay.
Wayne or Solani, yes?
Okay. All right. Okay. I think what Solani and Marcus meant was by lightly loaded is when your customers that only draw load and not contribute and who don't generate, when they are at their lowest, and your generation is at the highest, then you get the biggest voltage rise. But so I think, Lewis, you meant if you have the actual amps, when the actual amps in your feeder is the highest, then you get the biggest voltage rise, which is I would say your best scenario is when you either have low generation and low load, or when you have high generation and high load, because there will be less current actually feeding upstream into the rest of your network. Yeah, that's
okay. I get you. Thank you. I now understand what you're saying. So basically, if we go back to our model, maybe that's where I need to explain a bit of this. So in your winter load, PDFs are actually basically used in checking the compliance of your initial feeder. But in the grid impact assessment study, you're using your summer load PDF and your DER per kilowatt PDFs, which means at this point, what we are evaluating is as your generation is actually increasing at the lowest point of consumption. So I don't know if that's how we carry out our grid impact assessment. So the voltage response is based on both the summer loads and the DERs. And the summer load is obtained if you check, I don't know, I didn't show that maybe. Yeah, here, we obtain it at the point of the lowest particular point of a low demand summer day. where we expect that there would be low loads, and therefore there would be, and at the same time there is a higher PV generation. So in that case, if we are modeling this, we know that, or rather, I think from background, the way you've explained, we expect that the voltage will be high at this point, since there's a lot of injection that is going into the network. So I don't know if that also explains something, or.
Yes, I think it says the same thing that I was asking.
Okay.
It's just that when you spoke about the grid impact assessment,
yes.
I thought I saw a line that says a full load, but if that's the approach, then
no, it's full uptake, not full load.
Okay.
Full uptake. Sorry,
okay, cool.
Sorry about that.
No, thanks for that.
Thank you.
Okay.
So, Tulani, the mistake that we made was thinking that Lewis had made a mistake. Was that correct?
Yes.
Okay, that'll learn us. Okay,
I think most of us haven't picked up on the summer PDF. So I think that's the thing that, yeah. Anyway.
Okay. Thank you.
Yeah, very, very sharp. Thank you for elucidating that. I have a question from Mondi. He says, do you consider conductor transformer thermal capacity as a deterministic variable or probabilistic?
We consider all the variables, including the conductor performance, the conductor loading itself, as the performance of the conductor as a probabilistic variable. So the assessment is based on okay, maybe I should. The assessment is probabilistic, but we consider them as probabilistic as well. I don't know.
I think Mondi was asking specifically if you're regarding them as the thermal capacity as a deterministic variable or probabilistic of the conductor and transformer. In other words, are you running a model on the capacity of the conductor and the transformer in the background as well, or is it just a kind of a single number thing?
No. It's a probabilistic approach, because in between we are running a Monte Carlo simulation. For each penetration, you obtain a response, each of the node and branch response for a given number of runs, and then you pick at a given risk level the performance of either the voltage or the conductor as well.
I think Mondi's asking if you're running an I²T sort of time series on the transformers and conductors. Mondi, if you are in, you're welcome to come in.
Yes. Hi, colleagues. Yeah, sorry, I haven't been around for a while. I'm happy to be here, and thanks, Lewis, for availing yourself, to present here at a short notice. The question here is exactly what Marcus is saying, Lewis, and it's basically to say, if you're looking at a conductor thermal rating or even a transformer thermal rating, you can consider it to be, let's say, 7 MVA or whatever the case, and that is a hard number, that you consider it to be. And if you, as you are running your studies with many loading points and whatever, then you find that you've got a certain probability of hitting that 7 MVA capacity, and that's where you throw your hosting capacity, right? That's where you draw your hosting capacity. So that's one scenario. Then another one is, now my question is, do you consider that thermal capacity? Do you consider that in your modeling? Do you model that as a hard number, or do you allow do you give it a certain allowance in a way you allow a certain level of overloading? And let's say you can say you throw your capacity when you have a probability of occurrence of above so much, like it doesn't become a hard number. It becomes a probabilistic value itself.
Okay.
Yeah. What?
No, currently we consider it as a static number. As you can see here, our transformer is rated like at 150 kVA. So
Okay, now okay, that's fine then. Yes, and maybe as part of your other work, and you can think about this if you want. To a conductor and a transformer has got a certain, you can overload it for a certain duration. And then so basically you can go back to your overloading characteristic that you have come up with, which is probabilistic, and say I can allow so much, based on the feeder characteristics that that probabilistic line rating. So if you can put that in to all of this, and that means now in your background you've got your feeder being probabilistically modeled in terms of its capacity. We do have procedures for probabilistic feeder rating. I think they are widely available even at SAIEE, and internally at ESCOM we also have some. So you can see if you can push that model at the back, and you see when you now run your DG probabilistic model, when you run your load probabilistic model, and all of these things coming together, I would really like to see what capacity do you come up with, what hosting capacity do you come up with? Because obviously I should think that it would be above 7 MVA, if you use that example.
Okay, thank you. I'll I'll put that into and see if I can do it. That's the way. Yeah.
Of course, Lewis, you realize that at the end of the day, everything is a model.
Yes.
Okay.
Okay. Yeah, sure.
And there lies madness, perhaps. I have a question of my own.
Okay.
It seems to me, the first thing is just a point that we're entering almost a new era where the end customer, in other words, the receiver of the power, has some sort of economics on their side, and they can adjust that economics, which then impacts the circuit design and so on. But the question is, what are those economics? Are we tracking that currently? Is somebody working on that to see, what are the kinds of things that a household will do? It's kind of an open question, but I guess it's part of feeling out this area. Then the next one is perhaps a cat amongst the pigeons. We're looking at controlling these networks, and the voltage compliance is a big thing. So regulation is important. But at the end of the day, with greater and greater levels of DOR penetration, surely the voltage regulation is almost becoming an irrelevant constraint, because all of these DER systems are doing their own regulation. Comment.
Well, it's always hard to comment after a heavyweight person says things and you're just listening. So anyway, on on the economic side, I'm not aware of any person who is actually working on it. Maybe we could, because this is my first year of the PhD. We probably would have to model such a scenario in a case where probably someone is getting is actually controlling a scenario where there is a demand response to it, and how if it's pervasive, how that can actually impact the design, the final design. But I'm not aware of any person who is actually doing that, unless Justice knows someone. On the side of voltage regulation, I don't know. I probably have no comment. Maybe the team here can help me there. It's
Just
becoming
it's a conversation almost, but as we are getting greater and greater penetration, is the need for regulation not reducing because the householder has taken control of that by installing their systems? So we kind of beating ourselves. We could end up chasing something that's immaterial.
I actually I think I get your point in terms of if there's a way you can control the final impact of the impact of DERs on the system, then. But the question would be, would you rather hope that that is happening and not do anything, or do something even though there's, the control is going on, people are self-regulating?
But yeah, look, anybody that owns a hybrid generation system is self-regulating. I see Mondi has got his hand up. Mondi, you're welcome to come in.
Yeah, interesting, interesting points there, and I hope that Lewis, you are just taking notes for some of them because I think they are going to help you. So I think Marcus, and I don't know whether Neto is going to say the same thing, but what becomes a limiting factor, on perhaps the utility or the distribution utility being, taking advantage of the DER on the feeder, whether it's on LV or MV, in terms of that voltage control mechanism. The biggest issue that I've seen is that these small scale embedded generators, these are less than, they are rated as, according to the grid code, they are given A rating. And they are not required to have that voltage control capability or volt-VAR control capability. So they can just, when the sun is there, then they just inject on the grid, and when the cloud passes, then they are not there, and they don't have to have that reactive power capability that would assist in stabilizing, the voltage on the feeder. So I think that's where now the biggest issue comes in, and you are still now required to have a capability to control that voltage, such that when that sun or whatever is being used is no longer there, you can still use some way to support the voltage when it's low, and pull it down when it's high. So that would be just one contribution that I have, but I think you have a good point there, and also I think the use of energy storage is one way that I think it was presented by Justice, where use of energy storage can actually be applied to improve this hosting capacity as well. So now coming back to exactly what Marcus you are saying. Thanks.
Thank you.
Yeah, thanks, Mondi. I think you touched on an aspect that I wasn't implying. So there are two sides to that. If you've got a DRR system, you've got regulation inside the point of common coupling, and also backwards to the point of common coupling, and they might be different. So your constraints with the household appliances and so on, are being regulated, but then there's also the thing backwards into the network and supporting network voltage. Nsido, do you want to come in with your comment, question?
I think Monday covered all of them, but I'm going to come with the disagreement that the limitation has to be there. I think in cases where you have customers that might have battery installed, then I think what Marcus is referring to, I think in that case, we can forget about voltage regulation. But for now, since there's still a lot of reliance on our own network, I think it's a requirement. Number two, the issue of reverse power flow that might occur across your distribution transformer is also a concern as well. And I see Lewis has pegged the voltage at 110%, but maybe it's going to have to be lower, depending if your transformer is either bucking or boosting, to allow for the voltage rise across the transformer or drop, depending. So, but in terms of what Lewis is proposing, I think it's a it's a step in the good direction in terms of you're increasing the hosting capacity in the network, and it will be welcomed by customers as they want to put more on it. And this gives us a way to assess the networks before you connect the first customer, in that there is an equitable share in terms of paying for the said upgrades, instead of waiting for the last person who connects and say, sorry, you have to pay for upgrading the entire feeder. And probably this is the manner of which is best in terms of calculating the cost up front. Thanks.
Yeah, thank you, Sito. Lewis, comment from you?
Thank you so much. Actually, I'm getting educated very well here. There are angles within which I never thought about. Yeah, in terms of the way he says, in terms of calculating the upfront costs, yeah, I think that's, I had not thought about that, like, like the relevance in that direction. Yeah.
Yeah, another question from my side, and it might be almost a word to the marketplace, is when you're talking about everybody wants a tool, you know, in order to make their problems go away.
Okay.
How far are you and your colleagues in producing or partnering on commercial products to make these problems go away? God, look, I mean, if you look at this audience, there are professional planners everywhere.
Okay.
And everybody is looking for a tool. We've got Vasu, Solani, Mondi, etc., etc. These guys are looking for, Nsito is looking for a tool. How far are we from having tools?
Specifically pointing towards what I'm doing. if you're looking at the development phase that I'm in, no, it probably a year or a year and a half, then we can see what comes out of that, because it's very dependent on the final, how the method performs when tested with other things that I haven't tested already. We have only carried out the testing with PV. But in terms of partnering, I think if we have a solid product, we can get that going. The center does that quite a bit. Yeah, we could have a product rolling out, at least for testing, or a minimum viable product for that matter.
Thank you. I see you have a further hand up from Mondi. Go ahead, Mondi.
Yeah, thanks, Marcus. So I think just still now on that issue about the tool, the other thing that we notice on these kind of things, Lewis, is that you find that it can work properly in an environment where you've got lots of data, you've got everything metered, and you've got this and that at high resolution, etc. So in our environment, with the data issues that we have, do you think this kind of approach, do you think it is possible? Do you think we can do it adequately, or are we going to have a machine that we can use, but then only to find that we don't have data to feed it, and therefore it becomes like you have a Ferrari, but you will never use its capabilities? Thank you.
Because our first test is based on residential load data, whose characterization is easy using the Hammond beta tool. I don't think it would be very difficult to apply, in the development of this tool, and data may not be a problem. I think what is just a challenge, at least at this point in time, is testing it on a variety of systems. However, I must note that one of the problems I'm having is obtaining, just as I think about it, is data specifically that is related to dynamic loads from South Africa, because you can obtain that from elsewhere in terms of EVs and so on and so forth, but it may not necessarily characterize what's happening here. So as you say, there may be a few data limitations here depending on the scope, or rather the expanse of DERs we would want to consider to test it with. But just based on PV and load, I think the limitations would now be based on our assessment of larger networks rather than based on the data itself.
Yeah, thank you. I've got a hand up from Vasu. I think this is the last question. Go ahead, Vasu.
Thanks, Lewis, for the enlightening presentation, and the rest of the team for the comments as well. Just to add to Mondi's question, or the reverse of Mondi's question is, what's the minimum amount of data that we actually need to get a system in place? You know, we've spoken about this previously in our load research chapter with regard to you know, a test feeder and, you know, stuff like that. So yeah, so what do we need at a minimum to have a good, you know, probabilistic model going, you know, Lewis, if or any of the other team, if you can maybe answer?
So based on some work that I've done before, I think if you have load data, say for customers, a number of customers, for instance, I worked with these DLR data, which had like 70 customers, but you know, with gaps in between. But at least I think, in my opinion, if you have a number of customers for a period of years, you can assess, you can use that to carry out different tests you want. As for this particular one, I would actually think, I don't know the exact number of, you know, the expanse of the data itself, but I would think maybe just data that is enough to characterize the load, to model a load for different customers would be sufficient. But that's an area where I'm with the experts here. So maybe they can help me understand the aspect of what is the sufficient data that can help us in load modeling.
Yeah, thanks. I think it's quite refreshing to sit in on a presentation like this. I have a similar feeling to what I had listening to Justice's presentation, where the future is quite apparent if you have the data. And you've usefully shown us the kinds of things that we need to be knowing. And that to me is a very exciting revelation. I've got a hand up from Justice. Go ahead, Justice.
Hi, thanks, Lewis, for the presentation, and thanks for the questions. I just wanted to just add on this question regarding data. I think the answer from my perspective will be in two parts. I think the first one is that the future that we're looking into, particularly in how power systems are evolving, we can't escape the need for data, more monitoring, and you know, we need to understand the new characteristics of customers, the characteristics of distributed energy resources, and the whole interconnected system that is behaving in ways, you know, that we don't yet fully understand. So the need for data cannot be more emphasized. So that's just the first part of it. Then, of course, the second part of the answer has to do with the capabilities of this tool, whether it's fully functional with data or whether it's crippled without data. Similarly to what we have been doing with the Hammond-Beta algorithm in terms of feeder design, there are some things that can be done to characterize customers, you know, getting them into groups and understanding some homogeneous consumption patterns and things like that in a way to simplify the needs for extensive data collection. So these kind of approaches can still be applied to such a tool, but we are starting to understand the extent of errors or inaccuracy that can come off from such approaches. So again, it points back to the need of detailed modeling, at least in understanding the new characteristics first, before we can go on to characterize customers and use, you know, grouped characteristics for planning tools such as this one.
Yeah, thank you very much for that, Justice. It's much appreciated. Folks, one of the things that we've seen here, and it's quite particular to this presentation, is the amount of comments and the amount of appreciation that has come through from the audience and the amount of time that has been spent in discussion. So, Lewis, I take my hat off to you and to the work that you and your colleagues at Stellenbosch are doing. If this is the caliber of what our universities are producing now, then I think we're getting well set up for the future. So once again, I must thank you and wish you good speed on getting these results out and getting tools to the marketplace.
Thank you so much.
Okay, and yeah, once again, thank you from Load Research chapter side for standing up. It is much appreciated, and our door is always open for any new findings that you may have. They are clearly very relevant to this group. So
I appreciate.
Please keep us on your dial, your fast dial.
Okay.
Thank you so much.